Okay, hadi başlayalım. Good. Good, let's start. Today we'll talk about a new subject, and that is the common data environment and level of information need. Okay, LOIN. But before that, of course, we'll talk about LOD. So these are the main subjects: the information management and reliability. So we will first look into that. Common data environment, the CDE, 4 stages of the CDE workflow, level of development, and level of information need. So basically, as so far you can understand that with BIM, we are trying to achieve a step with BIM and ISO 19650. We are trying to achieve a workflow, okay, a way of working, and in that way, we are trying to standardize the way we create information and liaise between different stakeholders and finalize our decisions. Okay, so in that regard, with this workflow, which is collaborative, this is the most important part. We are following a collaborative workflow. We want to manage how this digital information is shared between partners. Okay, and in that case, we're using a common data environment, CDE, and we also define the reliability of the data. In that case, we have standards like LOD or LOE. Okay. The common data environment will explore how the teams collaborate using common data environment, which is the single source of information in the project. Okay. And there are digital containers, and there is a strictly managed through stage. Okay. So work in progress, shared, published, and archived. Okay, so we have 4 states which we will talk about. We'll talk about LOD, which is the earlier, let's say, understanding of how a, let's say, BIM object is enriched with data and information. So we'll talk about LOD 200, 350, 400, how it works. And then also we will talk about LOIN, which is a new, let's say, way of approaching this process. It's based on ISO 19650 LOIN framework, okay, where we balance the geometric data with the alphanumeric data level of information, okay, again, and the documentation, so that we deliver the right amount of data at the right time, so we don't want to waste information too. So, because sometimes too much information at the wrong time is not good, okay? So, this is the overall view of today's class. So we have different stakeholders, we have architects, we have engineers, we have contractors. And then they basically use a single source of truth, which is the common data environment, CDE. Okay? This is a central hub, and it connects the teams. And we have different gates in this process. Okay? Work in progress is like preliminary data. Shared, published, and archived are different stages, which we'll focus on. And in that regard, in parallel, we have, let's say, different stages of development of detail. Okay, so again, we will talk about that. So let's first try to explore the need. Why do we need to do it this way? Okay. As you know, before BIM, the traditional, let's say, workflow was fragmented. Okay. As a result, we have poor, unstructured information, and this causes errors, delays, and financial waste. So we have mentioned that many times, right? So we have fragmented communication between different people we have uncoordinated two-dimensional paper documents, right? So in traditional construction. And this is causing us costs, delays, legal disputes between people. So we receive let's say, requests for consultancy from companies. They always talk about that. So they are like, well, we mentioned that to them. Like, but how did you do that? Well, we called them. A call is not recorded. You have to be doing it in writing. Or sometimes they say that, well, we wrote that. When? We don't remember. Where is the document? We don't remember. Can you find the email? No. So this happens all the time. Sometimes different contractors, even though they are right, they basically they cannot find the information. So there is another thing. There is poor information. The information can be factually correct, okay, but it is unsuitable because it's untimely, incomplete, or it's given in the wrong format. Okay, again, like CAD drawings, two-dimensional, let's say, representations, or Word documents, they don't work. So we need strict digital standards. Otherwise, we lose money, we waste time and energy because we need to do manual corrections, okay? Because the unstructured data, it needs to be, let's say, fixed, corrected. And when you are trying to solve these, you basically are dealing with uncoordinated delivery teams. Okay, so we have many people, but they are not working together in the right manner. So, yeah, we have architects, we have engineers, we have contractors, and they're working in silos. They have their own, let's say, closed systems in traditional working, and then and their own, let's say, documents are understandable by their own software or their own, let's say, processes. And as a result, we have like emails, we have paper drawings, we have web-based systems, but still there are documents in these web-based systems. They don't work fluently, okay? So all these people basically are blocked by these, let's say, lack of flow of information. Information doesn't flow easily. And it's not reliable. You don't know. I mean, you have a document, you don't really know if it is the up-to-date document, if it's the latest version. How does it work? It doesn't work. As a result, we are paralyzed by the manual data. Like there are mountains of paper, and we cannot find what we need. Okay, in a large project, this is exactly the problem. And of course, if you find a clash too late, then it is a disaster. Your whole construction job fails. Okay, so you don't want that. So with BIM, of course, we are moving from unmanaged drafting. This is the past way of working. This is unmanaged drafting. Okay, we are making drawings, we are making documents, but they are not managed. They are a complex, let's say, chaotic situation. We are moving into highly structured information management. As a result, we are establishing trust and reliability. So that is the idea. We want to establish trust and reliability in information. Okay. So basically, we move from unmanaged CAD to a new process where we have clear roles, clear responsibilities, and authority on how the data is created and project data is created and shared. Okay, so we have different project teams, and these different project teams basically establish specific information requirements in the early stages. So you basically, it starts with the client, of course. Okay, the client first basically describe what kind of information they need at different stages, and then teams basically promise different types of information at these stages. And as a result, we implement good information management, which also improves financial performance. It reduces the risk, and it ensures that the final building basically meets the client's needs. Okay, so because at the end, we want to give the client a building that works, that is perfectly designed and that works, as needed. So basically, like in the past, traditional method, we had unmanaged CAD and paper. In halfway through, this is halfway through level 1, okay? In level 1, we have some 3D concepts, we have 3D models, we have web-based collaboration tools. There were, and there are still some web-based collaboration tools which are used for exchanging CAD documents, files, okay, or PDFs. But that's not what we want. We want to have a federated two-dimensional data model, which is, again, in a common data environment, okay? So we are trying to achieve that. So what is a common data environment? Basically, common data environment is the agreed and secure digital hub, which we use to collect, manage, and disseminate all approved project information. So it is a place where we load different pieces of project information. These can be the models, these can be some documents that needs to be attached to the models, these can be some, let's say, geometries, etc. Okay? And basically, in the CD, we bring together the models, the schedules, like lists of elements, or timing information, or again, PDFs, together through a managed process. So there is strict control and ownership. Basically, there is an author for a file or an object, and that person could be an architect, could be a civil engineer, could be a mechanical engineer. They hold ownership, and they have basically full authority on the file, okay? But they basically share them with people. People can contribute to that by asking questions. They can then withdraw them back, make changes, and share them again. Okay, so that's how it works. The CDE, in that regard, reduces time and cost of coordinating information, and as a result, we have the audit trail of information production. Audit trail is important. What does this mean? Let's say our project takes like 2 years to complete, right? So you want to know who submitted what model and what kind of changes that person did to that, or who did they transfer to. Maybe we have changes to people, okay? In the project, an architect, in the team of the architect, there may be many people coming and going. They can take over responsibilities of the previous people. But you want to know who did that. Or you want to know when they did a change, okay? So we have an architectural model, we have structural model, we have mechanical, electrical, plumbing model, okay, MEP. So it goes to common data environment. First, it is work in progress, okay? Then it is shared. When it is shared, it's shared with all the people, the contractor, the client, okay? Then, if everyone agrees on that, if there are no problems, and if the model is, let's say, mature enough, then it is published, okay? When it is published, then you can create COBI, you can create IFC models for different purposes, like for the operation, for instance. And then it is archived. When it's archived, what we know is that we have this full history of the project. From the very early stages till the last moment, everything is somehow captured, okay? So, like when did they submit, when did they pull it back, what changes did they make? It is a very, very big database. But the way it works is that because we label everything with these stamps, okay, nothing gets mixed up. But of course, at the very beginning, we have to agree on what we are dealing with, how we are dealing with that, okay? And of course, in that regard, this is the definition of reliability. So what kind of information do we want? Okay, what kind of level of information that we want? So basically, we want to prevent miscommunication and information waste. Okay, so we have specific frameworks for that to dictate exactly what data is required. So what is needed at any stage, okay? The first one is level of development, okay? This is an old one, we'll talk about, but basically, level of completeness to which a digital model element is developed. Like, how complete is your wall? How complete is your column, okay, in terms of information content? Basically, it allows people to understand how much they can rely on the geometry of that element. But geometry, what they found out was that geometry is not that, it's critical, but it's not the only critical thing, okay? The other critical things are like the information that we can embed in the model. So, ISO 19650 basically established that framework. It defines the extent, quality, and granularity of both geometric and alphanumeric data for a specific task. So, what kind of geometry do I need? What kind of information do I need at a given stage? Okay, so that is what it is dealing with. The reason is, if someone gives us too much information up front, then it is information waste, and also it makes things more difficult. So you want to receive the right amount of information at the right time. Okay, so you don't want to risk, you don't want to burden the project modeling with too many details. Okay, but also you don't want to risk the project by delivering too little data. Okay, so this is why we have LOIN. LOIN is in that regard important. So LOD versus LOIN, from design intent to fabrication. Basically, with LOD 200, we describe the column as a very simple geometry. It's a placeholder. It basically creates a space for the column for the future. With LOD 400, you have the column in high detail. It's enough to manufacture the column. Okay, so that is the idea. And with LOIN, we basically define the minimum required data. Okay, and basically reliability and reality. Basically, with the from 200 to 400, the amount of detail, the amount of information increases like 5 times or 10 times. So let's now focus on common data environment. Basically, it is an agreed central information repository. It's a central digital part where we collect, manage, disseminated all approved project information. So project information needs to be approved at different stages, okay? So, in the past, we had emails, we had physical filing cabinets, we had like shelves, etc. So it replaces that. We have a single, reliable source of information, a digital one, okay? And there are two parts. We have a workflow, okay? The processes where and rules we use to manage data, okay? So how do we fill the CDE, okay? And the second one is the solution, the actual software technology. We will talk about some different software applications. Okay? And by using the CDE, basically teams reduce the time and cost of producing coordinated information. Okay? So we basically prevent duplicated efforts for, let's say, replacing information. So in the past, the information was basically in a tangled silo. Okay, so we had all kinds of different files. We didn't know which one was the most recent one, which one was the one that we agreed on, etc. So it's what we call information decay. Okay, we have a massive data loss from design to construction. Okay, but with CDE we have a central data repository. Okay, it's a little let's say solution where we have a single source of truth. So everyone basically work together through CDE. We resolve clashes virtually. The synchronization is streamlined, so many different teams basically synchronize their data at the same time, and as a result, we have clarity. Okay. Before that, everything was cloudy. We didn't know which data was up to date and necessary. So for that, we use something called information container. Okay. In CDE environment, we have something called information containers. These containers are named persistent sets of data. Okay. Basically, an information container can be a 3D model. It can be a data schedule, like a list of elements. Okay. A schedule. It can be a database of spaces. Okay. Or it can even be a PDF document or even a video clip. Okay, so information container in that regard is a very wide definition of information. But the thing is that these containers are categorized into structured data. Okay, basically we basically define them in a standardized way. Okay, so let's say the projector in this room is related to this space. It's in a container. And that container can include, for instance, the information container for the projector, can include the user manual for the projector, can include the purchase details of the projector, can include the 3D model of the projector, can include the specifications like how much light it can project. Yeah. So everything can be included in the information container. And every container is given a strict unique identification code. Okay, so at the beginning of the project, we describe how we are going to define these information containers. Like in this case, for instance, you can define the projector as, let's say, mobile assets. Okay, in this building, it's a mobile asset. Or it can be fixed asset, actually. It's not moving, it's fixed. You can define it as fixed asset. And then among fixed assets, you have audio-video devices. And among audio-video devices, you have video devices and the projectors, screens, or computer screens, TV screens, etc. So among projectors, you define this one as a unique item. Okay, so this is how it works. Basically, it is a silo. You have a unique ID. And it can include any kind of information that you need, because we need to be able to relate these to objects in the model. Okay, so in that regard, we have ways to model. Okay, so it's one single source of truth that is a digital shipping container that includes any kind of, let's say, information. Because it's not only the geometry that we need for this projector. We also need the user manual. We also need the purchase let's say, details. We also need the maintenance, let's say, information. How often do we need to change the filter for this project? We want to know about it, okay? And all these are included in information containers. So, and we have metadata, status, and revisions. Basically, in common data environment, we have metadata, okay? Data about data, which is metadata. And it basically tells the users what the information is, how old it is, and what it's going to be used for. Okay. For instance, the user manual for the projector is needed for the operation. Okay, and it's used for basically operating the project. So, I am the lecturer here. I should have access to the user manual as a user of this building. In this common data environment somehow, okay, in the future, once the building is established and working, okay? Or, let's say, installation data. This means that projector is not in the room yet, but during the construction, someone will need to access that installation data, okay? So they basically can access that data and use it to install it properly. This is a problem, right? Like we always complain. No one reads the manuals, no one follows the procedures, people basically make mistakes. So we want to avoid that. Each information container has a revision code. Okay, if you make changes, the revision changes. Just like the syllabus at Auto class, it's now version 4. Okay, for this course, we have different versions of syllabus. We update, we put a new one. Now the new one is uploaded, it's version 4. Okay, so a revision code, so that we know if we are working with the latest version. Each container also carries a status code. Okay, how suitable is it? And what is it for? Is it for review? Is it for construction? And basically, the information container is only used for the particular reason that is put there. Okay. For instance, if we are dealing with a symbolic representation of the projector, it could be just a simple box. Okay, the size of the projector and its distance from the ceiling. Okay, that one could be a very simple geometry, and it's only for coordination. Okay, so you don't use it for construction. You can only use it for coordination because it's a placeholder. That projector is just a simple box. It doesn't have any electricity connectivity in the model. It doesn't have any real details. Maybe real details will make it like the cables for this one are coming from back. Okay, maybe the actual projector has cables coming from top. Okay, so you cannot rely on this model, but you can rely on it for coordination. For instance, you know that you cannot put a pipe that goes through here. You know that you cannot put a air duct here or a lighting fixture above it. Okay, it's because projector is there as for coordination. So this metadata, the status code, is in that regard very important. Okay, because we will replace the projector many times. We will first start with a box, then we will put the high detailed version, then we will put the documents like operation manual, installation manual, etc., and maintenance manual. And these are all coming with their own information containers and also their own status codes. So yeah, like that. So we basically have different codes for different purposes, and these different purposes are basically labeled on the information container clearly. Okay. Now the other thing is that, as I mentioned, the common data environment works as an audit trail. Audit trail means that you can go back in time, and if there's a problem, okay, like let's say that someone came and installed this projector, but they put the cables are coming from here and connected from there, but they put the cables from the wrong location, okay, or there is something wrong with it. Then you can always go back and check if the cables were properly represented in the model, okay, or if that information was given. If it was given, then it is the mistake of the builder. Okay, if they were not given, it's the mistake of the designer. Okay, so we need to figure that out. So for that purpose, we have a continuous journal of information transactions. Basically, we record the name of the user, the date, exact time, that information container transition, and also the information container transition. So when did they access that information? Like we can even see if the contractor has accessed that information. Okay, we can even see if that information was changed after the construction personnel accessed it. Okay, maybe someone changed data, but they didn't the contractor didn't see it. Okay, and in that regard, we need to have a very full, transparent audit trail. Okay, so this basically shows how the model is developed. Okay.
Hocam, are these CDEs cloud-based or embedded?
Cloud-based. They are all of them are nearly cloud-based. But it's a very good question. We will come to that in the upcoming slides. But based on your project, you can have modules for these CDEs that are working on your own servers. So sometimes some projects are, for instance, you are building, let's say, nuclear power plant. A nuclear power plant is a strategic building. It's very strict. You need to strictly secure the data. You cannot disclose it. There are some, of course, there are security problems, in terms of safety of the plant. But also there are, for some plants, there are also, how do you call it? Certain types of information, intellectual property. Okay, you don't want to give away your intellectual property. So it's a secret. The project is a secret. Okay, you only want to deliver, but you don't want to expose it to the world. Because, again, safety of the online repositories is another thing that you have to consider. Okay? So, there is traceability. So, when there's traceability, everyone works fine. Okay? When you know that, you can rely on the data that is there, and you can prove that you reached the data and used it, and it was there at the time, then it makes things much easier. Okay, so every action leaves a digital fingerprint. Like you open the file, you upload the file, you change the file, you make new alterations. It leaves a digital fingerprint. We have gates, work in progress, shared, published, construction. So we have different gates, and data flows through managed approval gates. These approvals are made by people. Okay, so when they make approvals, that is recorded too. Okay, and we have one federated model that is uniting all disciplines. It's a model that all disciplines are basically embedding their models. Okay, then of course, as the project timeline continues, the precision increases, the amount of data and information increases. So this is what we are trying to achieve. And of course, there are access rights and data security. Basically, CDE protects intellectual property and limits liability by strictly controlling who can see and edit specific information. So this is where your question comes to mind. Basically, we have controlled access at the information container level. So only limited number of people can access some information. Okay, not everyone can see everything. Okay, I'll give you one example. Remember, I told you I was trainee, summer practice. I was doing my summer practice at the Ticaret Bakanlığı building, which was Halkbank building. Okay, in the past, and Halkbank building was like below the ground. There are like 6 levels or something. At the very bottom, there is a huge safe, like the safe for the bank. It's still there. It was a bank before, now it is a ministry, okay? It's now Ministry of Commerce. Now, we were allowed to go visit these spaces. We could, and that safe was incredible. It was very thick walls, of course, it was also the foundation and everything. And I was able to take a copy of the whole building drawings, a printed copy, and leave the site. So, and I had my own copy of the whole building. So, think of the security. I mean, I was a trainee, and I had my own copy. And I left it at my friend's house, and I don't know what happened to it. So, think about it. It's lost. And it's the whole building plans, drawings, everything about that building, like a very thick one, A2 sized drawing sets. It's somewhere. Maybe recycled, maybe someone has it, but that friend went to US and I don't know what happened to that fund. Okay. So, in the past or in the traditional way of working, everything can go everywhere, okay? But with this system, okay, you have controlled access. Only limited people can reach sensitive data, okay? So you can basically control that and you can figure out. Authors produce information, but they can control and check. So, as an architect, you have full control on architectural model. As a structural engineer, you have full control over the structure. Okay, and architect's model is shared and it's reused by engineers, but architect can change anything there. And when they change it, engineers are notified. So, we have roles, like architect can read and write for the architectural model. The structural engineer can only read, can only view the model, okay? And permissions are, like in this case, by discipline. And in that case, architect's model is used to create structural model, etc. So we will have we will have examples of that in tutorials after the midterm, okay, towards the end of the semester. So we have an information steward, that's what we call a BIM manager. This could be a career plan for yourselves. Okay, think about it. You can be a BIM manager. So it is one career option for you. A BIM manager is very powerful in that regard, and it's a very well-paid job. It's a very stressful job, but if you do it well, it's a very well-paid job, and it's quite good. I would suggest you to look into that. Okay, a career option for you is BIM manager, because they are looking for BIM managers everywhere. You need to get training for it. You need to get certifications, which we provide at METÜ, myself and Ali Murat Hocam, Tanya. And basically, you can become a BIM manager, which basically controls all that. Okay, who can access what, where, how can we make sure that information is in correct locations, like work in progress or published. You know, we decide on that. Okay, but for all that, of course, we have all kinds of, let's say, methodologies. So there are, I think, 7 of them are here that I gave, or 8. There are commercial products for common data environment. So it's not only Autodesk. Autodesk Construction Cloud, it used to be BIM 360, is a cloud-based platform. Okay, so it works with Revit, Civil 3D, AutoCAD. We have ProjectWise. It's developed by Bentley Systems. Okay, it's again engineering project collaboration for large-scale infrastructure or civil engineering projects. It integrates with Bentley's MicroStation. Bentley MicroStation is another BIM authoring tool. Okay, like Revit. We have Aconex. Aconex was an individual company. Then it was bought by Oracle. Or you know Oracle, one of the biggest companies, the biggest database company in the world. It's a cloud-based project management and common data environment platform. It's owned by Oracle now. Provides document control, workflow management, BIM model management, large commercial and heavy engineering projects. There are projects where we can see like underground metro stations, underground tunnels for metro lines. These are all governed by Aconex. Aconex was used for İstanbul Büyükşehir Belediyesi metro projects. Okay, they have been using Aconex for that. Then we have Trimble Connect. Trimble Connect is again a cloud-based collaboration platform by Trimble. Trimble is quite an important player. Okay, I think they also now own SketchUp. SketchUp should be Trimble. SketchUp used to be Google. Did you know that? When it was the first time I used SketchUp, it was year 2006. That was when it was around that time they invented it. Google invented SketchUp, and they believed that with they gave it for free, and they thought that people would create models of the world, elements, and then they would put it on Google Earth. So we would have a digital model of the Earth. And then Trimble bought it. So yeah, Tekla Structures, SketchUp can all be integrated. Then we have A-Site. It's a standalone cloud-based CDE. Again, it works with IFC, like OpenBIM. We will talk about IFC, I think, 2 weeks later, just before the midterm. We have Dalux. Dalux, I think it's from Denmark. I'm not very sure. It's a very, again, one of my students worked on it, and they say it's quite good. Yeah, it's a software platform providing CD functionalities with an emphasis on field execution. Yeah, mobile model viewing, issue tracking, augmented reality applications. Like you use your mobile phone, tablets to manage the project. Okay. Then we have Bricsys 24/7. Again, cloud-based document management collaboration platform by Bricsys. Role-based access control, workflow automation, and viewing of 2D, 3D CAD files within a browser. Okay, now let's look into these 4 stages of information. Okay, workflow. Basically, in the CDE, we want to have distinct states for the information, okay? For development, visibility, and reliability. Basically, they could be, these information containers, okay, can be like 3D models or 2D documents, like I mentioned, can be 3D model of the project or the manuals in documents. They pass through a structured workflow states. Work in progress, shared, published, archived, okay? So, from one stage to another requires strict approval and authorization process, which we call control gates. So the BIM manager makes sure that this work in progress can be moved to shared, or shared could be moved to published, okay, or archived. So it's a highly structured flow, okay, so that members are collaborating effectively, okay? And of course, we don't want to use accidental use, we want to prevent the accidental use of uncoordinated or unapproved design data. So we don't want the structural engineer to use an architectural model which is, out of date. So we want to make sure that we have the right ceiling height, we have the right space defined, etc. Okay, so we don't want the structural engineer to use the wrong one. Okay, so work in progress is only for your own needs. Okay, so our architect, it's basically architect works with the work in progress. Then we have check, review, approve gates. Then we have shared states. Okay, so basically we verify if this meets the standards for collaboration. So we want to make sure before we share. Then we share. Okay, then the lead appointed party verifies if it works perfectly, because different, let's say, stakeholders, structural engineer, mechanical engineer, electrical engineer, they all check. And if it is okay, then it's published. And we have an archive at the end. Okay, so this is the idea. It's a linear process. Let's look into work in progress. Basically, it's the isolated native authoring environment where the specific task team develops their unapproved design data. Basically, this is like, as an architectural team, we are working on our own work in progress. And even within architectural team, we can have different work in progress zones. Because we can break down the structure into different spaces. And we can make sure that one team works on one space, the other one works on another space, and they don't basically see each other. We can do that. Okay? So work in progress in that regard is not only related to one discipline. It can be within different teams in that same discipline too. Okay? So they should not be visible or accessible to any other task team. You see task team. The task team for studio design, task team for canteen design, for instance. You can do that. Okay? So this provides a private workspace for the discipline. Okay, so that we can draft, we can model, we can experiment, we can make any kind of changes we want, because no one will bother us. It's our own place. It's a playground. If you want to move your model out of work in progress, okay, you have to formally check, review, and approve, so that your model is working with the project standards and procedures. So what do we want from us as a designer for the studio? Maybe before it's shared, we want to make sure that if the windows are clearly, designed, if the walls are clearly designed, if we have, let's say, a layout, etc. So there could be rules. These rules are given to us before we start the project design. Okay, so we know what we need to finish. And we give a finished model. Check, review, approve. So this is our playground. Okay, so we work basically in our sandbox. We can do whatever we want, and this is work in progress. We make experiments, we basically work behind the closed door. Only we give it to the shared model if it is checked, approved, and validated as fit for coordination. Is it good enough for coordination? This is what we are trying to understand. The second one, shared, coordination model. The shared state provides a secure collaborative environment for multidisciplinary teams to coordinate their models constructively without altering each other's work. Basically, we want to have different teams share their models so that they can come together and create an environment where we can work. So basically, once the work in progress is checked and it is ready to be shared, we push it to the shared area, then other people can consult them for spatial coordination. Like, for instance, you give this, and then the structural engineer checks if there's a pipe, if there is a window where there should be a column, or if there is a door where there should be a column. Okay. So basically, shared information containers are visible and accessible to all other teams. Okay, like structural engineering, mechanical engineering, chemical engineering. Okay, but they are not editable by them. So the engineer cannot change the place of the window. Engineer will only complain about it. Okay, or the mechanical engineer cannot change the lighting fixtures. They can only complain about the pipe going through that space. Okay, so if there is an error or a spatial clash, then it goes back to the work in progress state. Okay, so the shared model is pulled back to the work in progress. Okay, so then you don't have any more architectural model. So this is the architect's model, is the read-only model. This is the MEP engineer. The MEP engineer uses the read model, and then in that model, they basically say that, well, we have a pipe going through here, well, we have a soft clash because we cannot make maintenance here, it's too tight, etc. Okay, so they basically check for everything. As a result, of course, we coordinate, we detect problems, then we save money in the future because once we make these corrections at the design stage, we won't have any problems. And state 3 is published, authorized. Okay, so basically, once everyone is okay, once the mechanical engineer says fine, electrical engineer says fine, everyone says fine, then it is published. Then it could be used for detailed construction, manufacturing, tendering, facility management. Basically, this is definitive. It used to be before that, before shared, it used to be tentative, it's prone to change, but after the share, it is definitive. Basically, it's contractually binding, okay? So approved for construction, this is what we say. Perfect, you can now start construction. There is no problem, everything is resolved. We are perfectly fine with the model. Everyone is okay. We can start the construction now. And finally, the archive, audit trail. Basically, as I mentioned, with the CDE, everything was captured, like every process was captured, and we put them in the database, so we can use it for long-term administrative and regulatory purposes. We can also create as-built information, like we make scans, we can also embed the construction data, the model numbers of things, the physical basic representations of the real thing. As a result, these are read-only records, they cannot be altered. We can have, let's say, a basis for our, let's say, future legal, let's say, disputes. So this is a digital vault. Okay, so in the digital vault, we basically have everything, let's say, secured, okay, in archive. Good. Let's have a break. Go get yourselves teas, coffees, and we'll continue once you come back. Okay. We will continue with LOD. Level of development. Now, level of development is an older concept, okay? Basically, the LOD stands for level of development, basically defines the reliability and completeness of the object, so how complete, and its visual level of detail, like how detailed is the object, okay? The level of detail the level of detail is about the graphical complexity of the model, okay? But level of development, so the same acronym LOD is used for both level of development and level of detail, okay? When we say level of detail, we're talking about the graphical complexity of the model. But when we say level of development, we are also talking about the geometry and the attached information. How much code is given into the attached information? Okay, so that is the idea. LOD describes the minimum dimensional, spatial, quantitative, qualitative, and other data included in a model element in that regard. Okay, so it establishes a common language. Okay, so that engineers, contractors, different people will basically be able to tell what kind of information they need from you at different stages. Okay, so. Just like this, you must have, well, you will notice that when you start using Revit, you will be able to access online models, online object repositories, okay? For instance, there is something called BeamObject. We'll talk about that after the midterm, but it's tempting to go and download all kinds of wonderful objects from there, okay? Like you can go, maybe you will find a beautiful Porsche car, okay? Beautifully designed Porsche car. But the problem is, Porsche could be like this chair, or a chair like this, okay? It looks beautiful, but what does it add to the model? Do we really need to see the chair like that, okay? Because we want to use it as a generic placeholder. Okay, we are not going to give this model to the furniture maker to make the chair for us. Okay, so we don't need it that way. It could be only exact outside dimensions and a simple representation, and that's enough. Okay, but it should be smart. It should be simple in that regard, but it should be smart. Okay, so a chair that looks like real, but it is like 15 megabytes. I made that mistake. When you put a 15 megabyte chair into your existing 5 megabyte project, your project becomes awful to work on. Okay, you cannot rotate it. Your computer starts, overheating, and it's only for a chair. I mean, you make the whole building, you design the whole building for 5 megabytes, but you put a chair that is 15 megabytes itself. Doesn't make sense, okay? So in that regard, the chair should be a generic placeholder, okay? But we want exact dimensions. We want manufacturer specifications, okay? We want, for instance, procurement costs. How much is going to be to buy the chair, etc. So simple geometry backed by exact dimensions, manufacturer specifications, guaranteed procurement costs. This is what LOD is trying to tell us. Okay, so at each LOD level, we also define what kind of information we want from designers. That is the idea. Okay, so basically we have core design LODs, LOD 100, LOD 200, LOD 300. Okay. These fundamental LOD definitions basically follow the design evolution of the project, okay, from conceptual placeholder, a conceptual mass, right? So do we have any conceptual models here? Yeah, this is a conceptual model, right? So this is, if you ask what is this LOD for this is LOD 100. Okay, so it is just a conceptual mass. Then it goes into accurate specific design components. Okay, for instance, this one is LOD 200. Okay, or near LOD 300. Not perfectly, but close to LOD 300. Okay, so, or maybe I can show you here. This one is closer to LOD 200. Okay, so that is the idea. Now, LOD 100, element is graphically represented with a symbol or generic representation. Any derived information like area or volume is purely approximate and used for conceptual planning. We will work on that, particularly on design analysis week. On design analysis, we will use a conceptual mass model. Okay, you will understand what I mean by that. But it is basically an empty box for the building. Okay, a rough shape of the building. That's LOD 100. LOD 200, the element is a generalized system or assembly with approximate quantity, size, shape, location, orientation used during design development. What you're doing in the second year studio towards the end of the semester is design development. Okay, so you're putting columns, you're putting windows, you're putting, surfaces, so that's design development. LOD 300 is the element modeled as a specific assembly that's accurate in terms of quantity, size, shape, location, orientation, making it suitable for traditional construction documents. So, if your model has, for instance, beams, columns that are exactly this shaped, if you have the exact dimensions, let's say orientation, if the windows have all these, let's say, the frame and the divisions, etc., which is good enough for traditional construction, then it's LOD 300. Okay? So yeah, LOD 100, conceptual mass. Like a line, like a box, that's LOD 100. LOD 200, generic placeholder. We talked about it last week. A generic wall. It is approximately 200 millimeter thick. A generic 200 millimeter wall. Where we put it, that's LOD 200. LOD 300 is when the wall has layers. Okay? When the wall has layers defined carefully. Multi-layer 3D assembly. Then we have advanced LODs. So these were core design LODs. Okay? But advanced LODs are for construction and operation. We have LOD 350. Basically, from contractor to facility manager. So contractor needs detailed models for construction process. Okay, for the building construction process. Facilities manager needs the model for facility management operation. Okay, so details from basically. So as the model transitions to the contractor and facility manager, LOD increases. The details that we include, they increase to support spatial coordination, fabrication, as-built verification. So as-built verification, like, did you put a Casio projector? Yes. Well, like, what is the maintenance detail? Put that into LOD 500. Okay. How did you move the cables? Cables are on this beam. Okay. Put it on LOD 500. Okay. So you know that this is how many holes did you put in the system on the wall? You want to know even about that. Okay. So these are all in LOD 500. LOD 350, specific interfaces, supports connections to other building elements. Some people say that LOD 350 is a mixture of LOD 300 and LOD 400. Okay? LOD 400 is the element modeled in sufficient detail and accuracy for actual fabrication, assembly, and installation. So with LOD 400, we can basically, we know everything about building, okay, on that element. We know how to create this window in the field. This is LOD 400. LOD 500 is after the building is completed. After that projector is put into place. We count. We have the model from LOD 400. It says that it's coming from there, but in reality it came from over there. In the LOD 400, the cable was coming from there. In the reality, it came from here. Not that of a big difference, but still a difference. Okay? Or we put these pipes, and we have these valves, pipes. Okay? Now, LOD 500, we also put the brand for the valves. What brand? Which maker? Which model? Okay? Who did that? When was it manufactured? Who purchased it? Okay. What kind of maintenance data do we have? All these are put in LOD5. Okay. As-built representation of the construction assembly in terms of exact size, shape, location, orientation, meant for long-term facility operations. In big projects, okay, what they do is they also request laser scans or copies of the spaces. So they want to confirm that, for instance, there is a structure, a steel structure. With the laser scanning, we want to know how much of deviation do we have from the project. 2 centimeters, 5 centimeters, 10 centimeters, we want to know, okay, because that's needed for the future. So, LOD350, the coordination interface, as you can see, the beams are exact geometry, and they are basically related to each other properly. We use generic base plates, and these generic base plates only verify if it fits with other beams and other systems. So basically, that base plate is used for instance, reinforced concrete foundation. Okay, so that's what we need. LOD 400, we have the base plate, we have all the welding and the holes and the bolts, everything is there. When it is manufactured on site, it's going to be manufactured like that. Fabrication is going to be like that. This is 400. Then we have LOD 500. It is manufactured on site, and there are some changes, there are some dates, there are logs. For instance, we want to know how much torque is put onto these bolts. When they torque, I have to tell you this. One time, we were asked to be experts for an ongoing legal case on a shopping center in Ankara. Okay, there was this roof made of steel frame. Okay, but the roof collapsed. No one was hurt, but huge economic loss. So we were asked to figure out what went wrong. So we also received portions of the roof cut and sent to us. So myself and a professor in civil engineering department, we worked on that case. And we found out that the bolts were not torqued properly. They were not even tight. So I don't know how they missed it, but they were not even tight. And we found out that only by finding the paint going below the bolts. So it was like a forensic science, you know, like detectives. We were looking into different parts, and we found out that the paint that was done after the whole construction, which is, you know, after torquing, was underneath the bolts, which meant that there was a gap there, which meant that the bolts were not torqued. In the construction sites, you torque the bolts. Torquing, you know what torquing is? You know, you tighten. And when you torque, there is a number. There is a machine that gives you the number that you torque, like newtons per meter kind of moment. It's moment, right? So it's a force that you put. Once you torque with a pencil, you put a mark on the thing, as a person who did that, okay? But also, you put it in the beam bundle. So you torque it, you put the pencil mark on it, you can make sure that on that site, this pencil is only used for this torque number, and this machine is always calibrated for that torque. And you know that that machine is used, that pen is used, paint marker. That paint marker is used, then when you come to the site, you check, okay, paint marker, this torque, then you put it on the beam model. Then you know that it is torqued properly. Okay, you don't have to check it again. Then we have model elements table. This is very important, and it's something that comes from the owner, okay? The project owner. What happens is that they basically create a standard matrix for different elements. You describe different LOD levels for different stages. So you want to receive different LOD levels for a model element at different stages. Because you have different systems developing at different stages. Architecture can be a bit further in LODs, like your architecture could be LOD 300, but your structure could still be LOD 200, okay? So things, they don't go in the same speed in terms of design. So for that, you create a model element table and you use a classification system like CSI uniformat, okay? For every component, like foundations, exterior walls, HVAC equipment. Basically, this table assigns a model element author. Who is responsible for the windows? This is the author for the model elements, and who will give me the LOD 200, LOD 300, LOD 400 windows in the process. So what stage? Okay, so you basically describe that in model element table. Okay, basically LOD 200 is a conceptual placeholder at milestone 1. At milestone 2, architect upgrades the partitions for the specific assemblies. Basically, it updates with the geometry, LOD 300, and alphanumeric data like the types of material, their specifications, their, let's say, construction sequence, etc. Okay? So, model element author, basically contractor, knows that this milestone is provided by this person. Okay? So that is the model element author. And of course, authorized users and contractual reliance. Basically, what can other people use the model for? As I mentioned, a simple representation of the projector can only be used for coordination. But for an LOD 400 representation of the projector can be used for construction on the site. Okay, so that is the idea. Authorized users. So each LOD identifies authorized users, and they should be reliable enough for automated cost estimating, for the scheduling, or spatial coordination. We can only rely on the accuracy of these elements consistent with the required LOD for that particular milestone. For that milestone, if we have LOD 200, we cannot base our construction process on that milestone. We should wait. We cannot start making decisions about construction. We should wait for the correct milestone, which is LOD maybe 400. Okay? So, this means that there is no dangerous misuse of information. So, I put this and contractor use it for construction process. That is misuse of information, and we don't want it. We don't want an LOD 200 model to be used for that kind of purpose. So, like that. Don't rely for fabrication. This is not enough for construction. Okay? Use it only for as a space holder. Now, the next thing is level of information. This is the last part. Level of information need is something that was described in ISO 19650. The reason that it was published and described is because in the past, people were asking for higher LODs at earlier stages, or people were preparing documents that looked like higher LOD, but it was not the right time. I mean, how can I say? For instance, you're a structural engineer, okay? An architect's design is still in LOD 200, but you are putting very highly detailed columns into the model directly, okay? So that is not what we want. If they do that, the whole thing becomes complicated. So we don't want to do that. Basically, we want to have the extent, quality, and granularity of information at any stage. we want to know what kind of information we need and why we need it. Okay? So LOD is focused on geometric progression. LOE basically recognize that information needs are variable and they depend on different users. So we want to make sure that we don't have too little information or we don't have too much information. The correct amount of information. Okay? So what is the minimum amount needed to answer a specific requirement or support a specific decision-making point? For instance, what is the amount of information that a structural engineer needs to be able to calculate rough structural system for this space at this stage? What do they need? Or what is the amount of information that a mechanical engineer needs to have a rough idea about the number of ventilation, let's say heating, cooling, and air conditioning ventilation system ducts in the space, for instance. Okay, so they don't need much, but they want to know a certain amount of information. So, if you remember at the beginning of the semester I mentioned, we want everyone on board at the early stages. We want the mechanical engineer to start working on the project as early as possible. So we want to give them the large space as early as possible. Okay? And that space doesn't need to be very detailed. The level of information need is, in that regard, quite low. So we want to make sure that it happens. Like, 100, 200, 300, but when do we need it? Why? Why do we need it? Mechanical engineer only wants to know the amount of air in the room and the amount of number of people in the room. Okay? And also the mechanical engineer wants to know where the building is situated and where you have windows. Okay? Rough definitions of windows. And who needs it? The mechanical engineer needs that information. Okay, from who? Architect. What do they need? That's information about the space. So that's why? So that they can make calculations and see how much heating energy they need to pump into the space in the winter. Okay? So, there are three pillars of LOI. LOG, LOI, DOC. Done. So, LOG is level of geometry. Basically, it's even like the LOG can be like one-dimensional, two-dimensional. It can be just a document. Level of information. What kind of alphanumerical content do we need? For instance, for a column, okay, from a mechanical civil engineer, okay, for a column, we may need only the rough place of the column, not even the size of the column. So that we can criticize. Like, if the engineer comes and says, well, I want a column here, I don't care if it is a steel column or concrete column, if it's a big concrete or a small column. I don't want that column. You know, it's a stage. I only want him to give me, or her give me, the locations of the columns, and they give me, without making many calculations, and I figure out that there is a column in this space. So I say, no, I don't want that column. Okay? Then, if it was other way, engineer would spend so much time on making the calculations, making the drawing, a perfect column in this room, all for nothing, because I would say no to it. Even if it's a beautiful column, I would say no. Okay? As long as the engineer tells me there's a column in this room, that's enough. So, that is the level of geometry. I want the level of geometry to be low at this stage. I just tell me where the columns are. Don't care what kind of columns they are. Okay? Level of information. What type of column? What kind of material do we use? What kind of, let's say, surface finish there is? We need that maybe later. Towards the end of the project, I want to know what color the column is. What kind of finish there is on it. What kind of surface I have on it. Okay? What kind of details? Will they look nice? Will it look industrial? Will it look purist? What is it? Then documentation. What kind of unstructured documentation is needed? Like formatted reports, PDF manuals, warranty certificates, etc. as I mentioned earlier. So yeah, level of geometry. For this pump, we have level of geometry. How detailed the geometry will be? Level of information, the material specifications, cost, weight, performance data, flow rate, intelligence. Then documentation, like technical manuals, warranty certificates, maintenance instructions, etc. So I want to be able to accept these. Okay? From 3D model to data resource. Why and when? Why the information is needed? When it is needed, the milestones, and who is acting upon it, and what the object is. So, why, when, who, what? So these are the questions. We want to know, we want to ask the right question. We want to define the element in that way, in the correct manner. We don't want to give what is not asked for. We will only give what is asked for. We don't want to give extra information. Okay? We don't want extra information. So, based on that, for instance, architect may only need generic space-claiming geometry, LOG, for a door during the early design, while the facility manager later needs exact warranty data and maintenance manuals, DOC, but minimal 3D geometry. A facility manager does not need the geometry. They only need the number of the door number, what was this one? I always forget.
3.
Is it 3? Okay, door number 3. And then an Excel sheet. It's a timber door. There are 4 hinges. It needs to be oiled once a year. The lock is this brand. If it's broken, you can replace that. The keys are that type of key, etc. Okay, so the facility manager does not need the geometry. Okay, we should be able to transfer that information to them in that regard. Basically, this framework, the dynamic framework of Lloyd, allows us to create customized, localized, and use case specific requirements for the project. Okay? Who, when, what, why, based on that geometry, based on that alphanumeric data content, based on that documentation. So LOG, geometry, LOI, information, and documents. So we want to include all that in the common data environment. And of course, based on that, we eliminate information waste because we don't want to put unnecessary details. Okay? If someone puts an object with unnecessary details, then there is a risk. Like this chair, it's 100 megabytes, of course, as I mentioned. Okay? It will make your project very difficult. You have over-modeled details. It loads the file size, the screws, so the collaboration textures, cause rendering issues. Excess perfection syndrome, it's called. Excess perfection syndrome. Your model should be good enough to provide why, who, what, when. Okay? Why do we need this model? Why, who, for whom, when, and what are we modeling? Okay, so you don't want that. You want this. It's only 1 megabyte, but it has all kinds of information that's needed. Okay, so I don't care about the beautiful chair. And of course, how do we connect Lloyd to the project contracts? Exchange information requirements. This is a very important document. At the break, I was telling your friends, we are now consulting. We are now helping a company to get a job. And that job is a huge job, and the employees, the clients exchange information requirements, EIR, which I mentioned in the second week or third week, I guess, is 1,700 pages. Like they define everything. I want this pipe at this time, I want this roof at this time, at this detail, etc. So they're all clearly defined. So the line will be clearly defined in AIR by the lead appointed party, the general contractor, so that they know exactly what geometric and alphanumerical acceptance criteria will be judged against, and we have information delivery specifications for that. So when you deliver information for different stages, as we mentioned, they are checked so that it meets the law. So remember, I was talking about the work in progress, shared, published. So these stages, how do they check it? They check it with this information delivery specifications. Does it satisfy the information delivery specification? So basically, the client sets the vision, they establish the exchange information requirements, task teams, they author the model, and they basically give the model, the project information model, as it basically delivers the information delivery specifications. Okay? Good. You're lucky we are coming to the end. Summary. Now, with BIM, we want to control how the information is exchanged, okay, and curated. And we use the common data environment for that. And we use LOD and LOIN to make sure that common data environment is used properly. Otherwise, if we didn't have LOD or LOIN, okay, common data environment would be full of junk. Because people tend to put junk there. People tend to design junk, okay? You should tell them exactly what you want for each element. Then they put the right thing at the right time. See, otherwise CDE will not work. One person's acceptance for detail, other person's may not be. Okay, so you want to know how well they have defined. And for that, in the common data environment, we have a controlled collaboration. Basically, we have these 4 stages: work in progress, shared, published, and archived. And the teams rely on verified data. Teams have access control. Okay? We have geometric reliability, LOD. LOD is still used because we define the development of, we define different stages in LOIN with LODs. We have tables, and there we describe what LOD we want. But this is overall LOIN. Okay? LOD is a way of expressing LOIN, we can say, in terms of geometry and information content. And then we have targeted data, LOIN. ISO 19650 defines the level of information need framework. Okay? So it balances geometric detail, alphanumeric data, and documentation, so that we have the exact information needed for decision, so that we prevent information waste. Okay? Good. I think this is the end of it. So this kind of tells you how the whole thing works. Of course, there are many different software packages at the background. There are many contracts that we comply with. But what happens is, as an architectural office, as a designing engineer, as a contractor, we promise that we sign contracts. And in these contracts, we promise that we will work with these systems. We basically read this 1,700 pages of documents given by the client, and then we give reference to that document. We say that in this document you mentioned this way, we will do it that way. Okay. In this document you mentioned working in this CDE, we will work there. Okay. So basically, this is how it will it happens. So it is. Then what happens is that this BIM process is overall a contractual thing. Okay, when you think of it, it is not just a technical thing. I think now you understand BIM is not equal to Revit. BIM is much, much bigger than that. Revit is only one tool. There are many other tools that help us to deliver that. Okay, so that's the idea. Good. Any questions? We are continuing with tutorials. As you know, tutorials are recycled from last year. Basically, this project that you're working on, last week you worked on the structural system. This week you'll look into the enclosure system. And the reason that you have this model is because I want you first get to know the tool, Revit, okay? Before midterm, you will finish that model. So we have 2 more weeks. The midterm is on the 15th of April, okay? We have 2 more weeks, and you will finish the model. Once you finish the model, you will know more or less how to operate in Revit environment. After the midterm exam, we will look into object creation, and then we will do analysis. Then we will do other different tasks in this environment. Then we have 5 more tutorials after this semester. Mechanical, electrical, plumbing, we will do that. Coordination, clashes, etc. So we will all do it. Okay? Good? Okay. Now you can take a break or start working on your tutorial, and I'll see you next week.